Hello everyone. Today we are going to continue solving another problem from LeetCode's top interview 150 problem list. We have so far done all the problems until the rotate array problem. If you haven't checked out my videos on those, please go to my channel and check them out. So today we are going to continue with the next one, which is best time to buy and sell stock. Okay. So let's read the problem and make sure we understand it. You're given an array prices where prices of I is the price of a given stock on ith day. You want to maximize your profit by choosing a single day to buy one stock and choosing a different day in the future to sell that stock. Return the maximum profit you can achieve from this transaction. If you cannot achieve any profit, return 0. Okay. So that seems straightforward. Basically, we are given an array of prices of a given stock on different days, and we are allowed to do at most one transaction, which is buy once and sell on a future day once. And we have to figure out what is the best combination so that we maximize our profit. Makes sense. Let's look at the examples they have given. Example 1, prices are 7, 1, 5, 3, 6, 4, and the maximum profit is 5. And that is achieved by buying on day 2, makes sense, and selling on day 5, which is a price of 6. So that gives us a profit of 5. Yeah, and I do not see any other combination which will give us a better profit, so that's the answer in that case. The second example is 76431 with a profit of 0. Oh yeah, this is an interesting example. Basically, the prices are always reducing, and so in this case, we wouldn't buy at all. And that is important or interesting because we don't have to buy. If there is no combination which gives us any profit, then we just basically not buy and not sell. Okay, the constraints are that the length of the array is between 1 and 100,000 and the prices are between 0 and 10,000. Okay, that makes sense. Let's actually figure out the approach before we try to code it. The first approach that came to my head as I was reading the problem was a brute force approach, right? Where we basically consider all combinations of a buy day and a sell day and figure out what is the profit for that combination. And if that is the better profit than what we computed for another combination, we basically make this our best profit or max profit. So just to illustrate that a little bit more, so for example, in this particular prices array, we would take all combinations for buy day and sell day. So if buy day is 1, buy day equal to 1, then sell days are 2, 3, 4, 5, and 6, right? 2, 3, 4, 5, 6. Yep. And for each of those combinations, we basically say, hey, what's the profit? And we keep track of max profit. Similarly, if the buy day is 2, then the potential sell days are 3, 4, 5, 6, and so on and so forth. And we just evaluate the profit for each of them and keep track of max. Very straightforward. This solution pattern will appear in a lot of array problems, will most likely not be the most efficient way to solve it. In this case also, it doesn't seem to be the most efficient way to solve it. But I do want to, since this is the first time we are doing such a problem, I do want to kind of implement that reasonably quickly, just so that we can compare and contrast that approach with the more efficient approach. So okay, so let's call this max profit all comps, combinations comps, and try to quickly code that. Code is pretty simple here. Basically, we keep track of max profit. Default max profit is 0. If we don't do any buy or sell transaction, then the default profit is 0. And there are many we have one loop for all the buy days. Buy day is less than prices dot length plus buy day. And then we have a nested loop for each buy day. We want to consider multiple sell days. So we have a nested loop of sell day. And remember, the sell day can only start from the day after the buy day. So buy day plus 1, sell day is less than prices dot length plus sell day. And then for that, we book the profits, or we calculate the profit, I mean, prices of sell day minus prices of buy day. So that would give us the profit for that combination. And if that profit is bigger than max profit, we just update max profit. Very straightforward. One thing to note here is that profit could be negative, and we don't have to handle that as a special case, because in that case profit would not be greater than max profit, as the default max profit is already initialized to 0, indicating that if we don't do any transaction, it's 0 profit. So negatives will automatically be handled. And here we say return max profit. Okay, so that is the approach. Let's try to call that approach the slow approach from our main implementation function. So return max profit all comps and prices. Let's try to run this and see if it works. Yeah, that should be straightforward to fix. Let's see, ILANGTH. Okay, it says accepted. Both the cases. In this case, profit is 5, as they said. In the second case, the profit is 0, as they indicated. There is one more test case I was thinking of, which I would like to add actually here, which is, although in this approach, like, it should work, but when we take the more efficient approach, it will be interesting to see if that works. So here, what I was thinking of is, what if we have 7, 13? And 1 for this. So the reason is because I wanted to check where the buy price is higher, or the highest actually, excluding 13, and still we can actually book more profit, and that case should also work. In this case it will work because it just dumbly tries all the combinations, but it's nonetheless a very good test case to have. Let's go to 3, and yeah, 6 is the right answer. Okay, so now that we have looked at how a brute force approach would look like, which considers all combinations, let's think of what a more efficient solution might look like. So while I was coding that up, I was thinking about one thing which will give us a good insight into what is the more efficient approach. And that is, like, let's again, take this array down here. And the thing I noticed is that, so let's say we are trying all combinations, right? But whenever there is a buy price, whenever there is a price which is lower than 7, like, after 7 we go to 1, right? And we basically have tried many combinations, many sell day combinations for the buy date to be second day, and we have computed the profit. But once we go to 5, we don't have to try any combinations, because, or any sell day combinations for 5 buy day. 5 is not a valid buying price because we already considered a buy price which is lower than 5, which has come in the past. So anything that we any day we sell for a buying price of 5 will never yield a profit more than buying at a price lower than 5, right? So that is why that brute force approach is very dumb in that way. It's also very simple, but it's very dumb in that way, that it's actually not taking advantage of that fact. And similarly, if we see a price which is lower, like, so for example 7 to 1, we can immediately say that, okay, hey, 1 is definitely a better buy price than 7, because 1 is lower, and anything that comes after 1, for example, if there was a 10, there's no point in buying at 7 and selling at 10, because between 7 and 10 there was a number which was lower than 7. So combining those two insights, we can actually come up with a little bit, or a much better approach. Let's call it max profit fast, for a lack of better word, prices. And the approach is as follows, that, okay, we scan through all the prices, and initially we say our buy price is potential first day's price, which is 7, and then we go to the next day and we see, is the price on that day bigger than 7? If it is, then we potentially have a transaction that can make us profit. So we calculate profit, and if that profit is bigger than the max profit so far, then we update our max profit. If the number that is after 7 is lower than 7, which is in this case, then it's okay. We have a better buy price. 7 should not be the buy price, because whatever comes after 1 will yield us a better profit by selling on that day instead of 7. And so that is pretty much what we do. We have just two cases. Every time we look at a number, we say, okay, what was the previous buy price? And are we higher than previous buy price? If we are, we calculate profit and update max profit if this is better profit. And if we are lower than the previous buy price, we just update the buy price. And that will get rid of all the redundancy that we had in the previous approach, like we talked about. So let's try to implement that approach. Just like before, we have to keep track of, sorry about that, max profit. So let's start that with default of 0. Then, like we said, we have some buy price, right? So initially that buy price will be prices of 0. Now, anytime I access indices of an array without checking the bounds of an array, I think of special cases, right? And in this case, theoretically, the function could be passed an array of size 0, which means even index 0 is invalid. And in this case, actually, they have given a constraint that the array size is at least 1. But in reality, I would generally add an if condition. Here, prices dot length is equal 0, then return 0 right away, right? Anyway, just something to think about every time you do something special. You want to make sure you're not really doing something invalid. Okay, so now we are going sell day is equal to, or this is not sell day anymore, it's any day. So day equal to 1, because we already looked at prices of 0 and that was our initial buy price. Day is less than prices dot length plus day. And like we said, we just have two cases, right? We have a case where, okay, prices of day is actually better or bigger than the buy price. In that case, all we do is we compute profit. So let's say profit equal to prices of day minus buy price. And then we see if that profit is better than max profit, just like before. Then we book that as the better profit or max profit. And otherwise, else of this if, we basically are in a condition where prices of day is less or equal to buy price. Equal to is not a big deal. It can go in the first if or the second if or the else part. But in the case where it is less, which means we have a better buy price. So all we do is we say prices of day. We update a buy price to the better one, right? And that is pretty much it. So yeah, I think that's the straightforward approach. We basically, like we discussed, just two cases. If we find a price which is higher than our buy price, we calculate profit and update max profit if appropriate. Otherwise, we just make that the buy price. And after the whole loop is ended, we would have found our max profit. Let's try to call that from our main function. And let's try to run it. Okay, there you go. So in this case, the profit is 6 in case 3, and in the test case that they have given, it's 5, and in this case, it's 0. So that all worked pretty well. One last comment on this problem before we end this is that we know this is an inefficient approach and this is the efficient approach, but it's always good to know by how much, right? Or what is the time and space complexity. So before we talk about time complexity, space complexity is order of 1 for both approaches. And the way to think about it, maybe it's really obvious, but just for completeness, is that no matter how small or big the prices arrays, if the arrays has 10 elements, 100 elements, 1,000 or 100,000, the amount of extra memory we use in addition to what we are given is constant. It's either 4 or 5 or 7 objects or 7 different memory locations, right? So it's constant, and that's order of 1. right? So no matter what the length of prices is, and same is true for this. So okay, with the memory complexity out of the way, which is order of 1 for both the implementations, let's talk about the time complexity. That's probably also obvious. Here there are two nested loops. The outer loop goes O of n times, and for each of the iterations of the outer loop, there is an inner loop which also goes in the worst case O of n times. Well, strictly speaking, it's n minus 1 because of this, and then n minus 2, and then n minus 3, and so on. But when we are talking about complexity, you always take the worst case, right, to compute the upper bound. And so it's O of n times O of n, which is O of n square. While in this case, it's just a single for loop, goes through all the elements of the array, and that's O of n. So there you go. That is why this is actually not only efficient, it's actually efficient, by a big margin, because it increases linearly with the size. The time it takes increases linearly with the size of the prices array, while this one increases at a quadratic pace. Okay, hopefully that was helpful. See you guys next time.